Hi everyone and welcome to another LIC class. In the previous class, we finished different type of filters, low pass filter, high pass filter, and band pass filter. And in this today, we will start a different application of or type of application of op amps, which are called the op amp multi-vibrator. So what is a multi-vibrator? A multi-vibrator is an electronic circuit that generates a square or rectangular wave pulse by rapidly switching between two stable states. They are used usually to create timers or generate clock signals, or sometimes they are used in an application what we call the PWM, or pulse width modulation, which is a very important concept. You're going to hear a lot about PWM, or pulse width modulation. It has a lot of application, both in electrical and electronics and power electronics, and in communication systems as well. These multi-vibrators are used to control the, for example, one application is to control a DC to DC converters, like a buck or boost converter, to control the clocking, to control the speed of a DC motor. It's used also for communication systems, for coding, and so on. So a multi-vibrator, again, it's an electronic circuit. It generates a square or rectangular signal, and it just switches between two states. It could be, for example, here we have a positive voltage. This could be between positive 5 volts and 0 volts. Or it could even be between a positive and a negative voltage, for example, between positive 5 volts and negative 5 volts. One other example for these type of circuits is in digital circuits. So for example, the state of 1 is the logic of 1, state of 0 is logic of 0. And we can create a clock to create control a register or a flip-flop or a timer or a memory or so on. We can also change the positive state and the negative state, or the 1 state and the 0 state. That's the reason we call it a multi-vibrator, a system, which, and this is actually a multi-state system. And by controlling these duty cycles, we can, for example, control the speed of a DC motor. This is one good example. Let me give you an example of how we can use this PWM, or pulse width modulation. Again, the modulation is based on the width of the pulse to control, for example, a DC motor. Imagine that we have an RC car, and we have a remote controller for it. The way that an RC car works, an RC car, we usually have a motor, which is connected to a receiver or a transmitter or a controller. The rotational speed of a DC motor is determined by its voltage. It's actually DC voltage. So if you connect a DC motor to a battery, you can control its speed by reducing or increasing the voltage. The higher the voltage is, you're going to have a higher speed, higher torque, higher power from the DC. Now, how can I control, and imagine this is a controller that I'm going to use. How can I remotely control the speed of a motor in an RC car or a drone or something like that? So the RC car has a DC motor, and I want to control it remotely. That DC motor is connected to a controller which there is connected to our receiver, and it's connected to a battery. So let's say this is connected to a battery, like a 12-volt battery. If the switch is only turning on and off, the motor will go from maximum speed to 0. If you just have on and off, you can just go to maximum speed, 12 volts, or you can go to 0 volts, or just, but sometimes you want to have control over your RC, especially if you have a drone, you have like a quadcopter or motor. If they just go between 0 and 100, the drone would immediately flip. So you want to have a control. You want to be able to control the motor and have, for example, the speed at 50%, 20%, 10%, or 80%. So how do we do that? We do that through what we call a pulse width modulation. Instead of turning it on and off, we turn it on and off at a high frequency. So for example, if 10% of the time the switch is on and 90% of the time the switch is off, we're gonna have this duty ratio. And in this duty ratio, the switch is 10% of the time it's on, 90% of the time it's off. So you may think, so in this case, the motor will work 10% of the time at maximum speed at 12 volts, and the rest 90% at 0 volts. But by adding another element, we can actually smooth out this transition and actually get an average of voltage. So for example, here, if 10% of the time is on, 90% of the time is off, what would the average of these two cycles be? It's going to be around here. Do you agree? It's going to be around like 10 to 15% of the voltage. For the second one, when we have a 50% duty cycle, the average voltage would be in the middle. You all agree? It's going to be around 6 volts. So the average would be 6 volts. And for this one that has a 90%, the average would be around 10 volts. So let's say here is 12 volts, 6 volts, and 10 volts. So what element can I add to store this power and to smooth out and get an average of this? I'm sorry? Perfect, a capacitor. Yes. So we have a high-speed switch. And if I can connect that to a resistor and a capacitor, what happens is now I'm actually smoothing out. And if I give it like a signal that looks like this capacitor is going to charge during the cycle and it's going to discharge. So you're going to have a voltage that is around the average of the time on and off. Now, by just changing this duty cycle, and this duty cycle is changed by the switching speed on how much I want to keep it on and off, I can shift this average. I can go to 0 volts and I can go to 12 volts, depending on how many voltage I want. If I want 6 volts, for example, I would keep it on 50% of the time and keep it off 50% of the time, and I'm going to have it 6 volts or which is in the middle voltage, average voltage. This is used a lot in what we call the DC to DC converter, buck boost converters, and you're going to learn a lot about that in power electronics. Also, we have this used in a lot of controlling just analog RC. If you want to have a remote controller, this is actually the way that we control a robot remotely. Yes.
Your picture on the right, it's got that minimum voltage there. So you have your axis
Here.
Yes, I never.
Yes, this one, again, you can have, that's a perfect question. You can have the stakes switching between 12 volts and 0. You can have them switching between 12 volts and 2 volts. You can have them switching between 12 volts and negative 12 volts. So this depends on you. The reason actually we use this is sometimes in digital design, we don't want this logic of 0 to be actually at 0 volts. We want it to be at 1 or 2 volts. The reason that we have this, and actually this is from a digital system, is that if you're controlling for example, an RC car or a digital logic gate remotely, we want to have distinguish between the logic of zero and the zero voltage. The reason is this. Sometimes in a circuit, when, for example, water gets inside, when it's circuit, the PCB board is wet, the circuit will be short circuited or grounded, and it will show us 0 volts in the output. Now the system doesn't know, is this 0 volts a logic of zero, or is it 0 volts? It's an error in the system. When you put a little bit of shift and your logic of zero is now suddenly half a volt or 1 volt, if the system is short circuited, then the system will realize this is not the logic of zero, this is a system failure, it's an error. So we usually leave a little bit of buffer in that system. This one is particularly for that case. But in most cases, you would have, especially for RC car, is switching between 1 and 0 volts, because we don't care about the logics. We don't want to convey or transmit any data. We want to just control the speed of the motor. If you have valuable data that 0 is the same importance as 1, then you want to keep this 0 logic of 0 greater than 0 volts. There's a difference between logic of 0 and 0 volts. Logic of 1 and, it's going to be 12 volts. Some systems 5 volts. You're going to learn more about this in digital design. And did that answer your question? Yeah. Okay. And sometimes it just oscillates between positive and negative voltage, depends on the application. So and by the way, the multi-vibrator, we can build it out of transistors. We can build it out of a 555 timer, but building out of an op-amp has a lot of advantages and pros, and I would mention them in this class. The op-amp multivibrator is a non-inverting op-amp, or you actually created it with the inverting op-amp as well, but mainly 90% of the time it's non-inverting op-amp that produces its own input signal with the aid of an RC feedback network. And this is a general op-amp multivibrator. So op-amp itself, as we learned, it's a very versatile device. It could be used as an amplifier, like a non-inverting or inverting amplifier. It could be used as a transducer to convert voltage to current or current to voltage. And at the same time, it could be used as an amplifier, so a transducer and an amplifier. Another application that we learned from using op-amps is to use them as filters, active filters. A lot of applications over there. Or we can use them as signal conditioners. But another application, a very useful application of op-amps is using them as astable op-amp multivibrator. And we mainly want to work with astable. We don't want to discuss bistable op-amps or circuits, because we don't have a lot of use for them. This type of op-amp multivibrator, the astable multivibrator, continuously switches between 2 unstable states without the need of any external triggering. The 2 unstable states that it has, usually it's between its positive saturation voltage and its negative saturation voltage. The multivibrator circuits, as mentioned, can be constructed using transistors, logic gates, or it could be used from a 555 timer. But there's problems when you use a transistor or a 555 timer. For example, transistors, you need a lot of other components like 10, 15. For an op-amp, you just need 3 or 4 components added to it. So in general, a op-amp multivibrator looks like this, and it actually oscillates between its positive saturation and negative saturation, between 2 states. Here it's between positive V saturation and negative saturation. The problem with using these components to produce an astable multivibrator circuit is that for transistor-based astable, many additional components are required. Digital astable can generally only be used in a digital circuit, and the use of a 555 timer may not always give us a symmetrical output without additional biasing components. But the op-amp multivibrator can provide us with a good rectangular wave signal with the use of just 4 components, 3 resistors, and a timing capacitor. So it's the simplest, most accurate type of multivibrator that we can build. We use an RC timing network connected using to the inverting input of the op-amp, and it has a voltage divider network connected to the other non-inverting input. Unlike the monostable or bistable, the astable multivibrator has 2 states, neither of which are stable, as it constantly switches between these 2 states, with the time spent in each state controlled by changing or by charging or discharging of a capacitor through a resistor. We can change this capacitor or the resistor, and I will show you how we can control these, the width of the signal, or the width of the output pulse. The main component of a multivibrator is, or in the heart of a multivibrator, we have an analog comparator. So as we know, gain for an ideal op-amp is infinite, and the gain for an ideal op-amp is actually V positive minus V negative, the total gain, times its gain. Oh, this is, we can say the output voltage. V output, let's put it this way. V output, or in other words, AV is V out, as we know, over V in, just a reminder. And V in is equal to V positive minus V negative. The input positive voltage minus the input. Therefore, V out would be V positive minus V negative times AV. So for an ideal op-amp, we know that AV is equal to infinite, very large. Therefore, if V positive isn't equal to V negative, or in other words, if V positive is greater than V negative, then V out would be equal to positive infinity. And if V positive is less than V negative, then V out would be negative infinite. But can an output voltage of an op-amp go to infinite, positive, negative? No. It's always capped at its saturation voltage, which is determined by its supply rail voltage. So when V positive is less than V negative, then V output would be equal to negative VCC. And when V positive is greater than V negative, then V out would be equal to positive VCC. So the comparator actually acts like this. When V positive is greater than V negative, V output would be the positive supply voltage. When V negative is greater than V positive, then the output voltage would be negative, the negative supply voltage. We can also connect one of the inputs to the ground. That will be our reference output. For example, here, V negative is connected to ground, which is 0. Then V positive, if it's greater than 0, then This is also for V positive greater than 0, and this is for V positive less than 0, because V negative is 0. So if V positive is greater than 0, V output would be positive VCC. If V positive is less than 0, V output would be negative VCC. But this creates a little bit of problem. When you have an open loop system, these systems are usually very sensitive into the changes on the input, because you don't have a feedback to correct the input. These systems are very sensitive to any changes, even the smallest changes in the input. Let me give you an example. Did you write this down? Can I erase it? Yes. Let me give you an example. Take this circuit, for example, and imagine that V negative is connected to the ground as a V reference, okay? So here, imagine that V reference is connected to the ground. So this is 0 volts. And this is connected to our input. Imagine we didn't even connect this to any input. Imagine this, it's connected to a circuit, and that circuit is creating a little bit of noise. Let's say it's creating a noise like this, without even giving us any output. And this is actually our 0 volts. Each time that this noise passes and goes above 0 volts, you're going to have an output which is equal to positive VCC. So here, when it's greater than 0, V in is greater than 0. And here, imagine V in is less than 0. And when it's less than 0, you're going to have something that looks like this. It's equal to negative VCC. So suddenly you have a lot of oscillation between the positive and the negative. So you're going to have a lot of distortion in the signal. You have a very small noise coming in, and you're suddenly magnifying it to a huge pulse signal. So these even small changes in the input, and I'm going to zoom a little bit, even these very small changes in the input, each time that it passes the threshold, so this here, the output will be positive VCC. Here it's going to be negative VCC. Again, it's going to switch. So it's oscillating between positive and negative all the time, which is not good. We want to have control over. We don't want a small noise to be able to disrupt our circuit. So how can we fix this problem? We want to use a competitor. The competitor is the basics of the system. What do you think we can do to fix this problem? Any suggestions? Capacitor. So if I put a capacitor, that's actually a good idea. A capacitor, actually what it does is acts like a filter. It creates something that we call in communication systems moving average, because you're going to average all of them. But it creates an additional problem. The capacitor, if you put it directly connected to this, it's going to act like a filter. Okay. Yes, it's going to block a lot of our signals. And sometimes those signals, especially for this is a, this system actually is a low frequency. And if you connect the capacitor in series, it's going to create a high pass filter. So it's going to block all the inputs that we have. Another option that we can use is simply we can give it a feedback. Feedback always makes our system stable. And we can create a trigger, what we call a trigger, a Schmitt trigger circuit. So to eliminate any erratic or uncontrolled switching operations. The op-amp used in the multivibrator circuit is configured as a closed-loop Schmidt trigger circuit. Consider this circuit below. Now, instead of directly connecting the reference voltage to um, where I was, sorry, but distracted for a second. So the only difference between this and the previous one is that in this one, we have a V reference, which the voltage is greater than 0 volts. In the previous one, V reference was connected to the ground. Now we have a V reference, which is equal to this V beta, the voltage here. Now, can you tell me what is this voltage? How can I calculate this voltage? Again, here, V reference is equal to V beta. Let me give you a question here. Imagine R1, and this is actually a small quiz. I'll give extra points for whoever is able to solve this. R1, imagine it's 5 ohms. And R2 is 20 ohms. Vn is 3 volts. No, just imagine we don't have Vn. It's better actually not to have Vn. What is V beta in relation to Vn and V out? I'll give you 5 minutes actually to find this. This is a type of inverting amplifier. I want to find V beta. What is V beta? No. BVN. Why do you know? I'll give you 4 minutes to find. And imagine V out here is 2 volts. Anyone has the answer?
here. Just read backwards.
What do you mean?
Feedback is just true as one line.
What do you mean by backwards?
A true gain would be R1 over R2, negative R1 over R2.
Imagine you don't even have Vn. You just have V out. And one thing that you have to keep in mind, I input for the op amp, ideal op amp is 0. So what you have is essentially you have this connected to this. This is 5, this is 20, this is ground, and this is 2 volts. We want to find this voltage. Yes. What is it, 1.6? Yes. So it's a simple voltage divider. V beta would be equal to 2 times 20 times 20 plus 5. So it's going 40 over 25 gives us 1.6. So the op-amp competitor circuit is configured as a Schmitt trigger that uses positive feedback provided by resistors R1 and R2 to generate hysteresis. As this resistive network is connected between the amplifier output and the non-inverting pulse input, when V out is saturated at the positive supply rail, a positive voltage is applied to the op-amp non-inverting input. Likewise, when V out is saturated to the negative supply rail, a negative voltage is applied to the op-amp's non-inverting supply rail. A negative voltage is applied to the op-amp inputs, non-inverting input. So the way, again, this works, it's very similar to the previous one. If Vn is greater than V reference, then V out would be equal to, can you help me on this one? What happens if Vn is greater than V reference? What is V out equal to? So Vn greater than V reference means V negative is greater than V positive. Am I correct? Vn is actually our negative voltage and V reference is our positive voltage. And assuming this has a very high gain, when V negative is greater than V positive, V out would be equal to negative VCC. When Vn is less than V out or V reference, then V negative is less than V positive. Therefore, V out would be equal to positive VCC. So depending if our reference voltage is greater or less than the input voltage, you're going to have a positive or negative voltage in the output. And this is the reason actually they call it the inverting amplifier. Inverting amplifier, I mean, if you have a positive input, you're going to have a negative output. When you have a negative input, you're going to have a positive output. So it inverts everything.
We went to the last slide.
The previous one. Now, as two resistors are configured across the op-amp output as a voltage divider network, the reference voltage V reference will therefore be dependent upon the fraction we can use the following equation for finding V reference. V reference, again, we're using a voltage divider. The V reference will be depending upon the fraction of the output voltage fed back to the non-inverting input. These feedback fractions, beta is giving as would be R2 over R1 plus R2. V out is equal to V saturation. Therefore, V reference would be V out R2 over R1 plus R2, or in other words, it's going to be beta times V saturation. Therefore, positive V reference is going to be positive B beta V saturation, and negative V reference would be equal to negative beta V saturation, where positive V saturation is the positive op-amp DC saturation voltage or the DC supply voltage, and negative V saturation is the negative op-amp DC saturation voltage. Let's solve an example. So first example, R2 is equal to 15K, R1 is equal to 10K, and VCC or V saturation is equal to let's say 5 volts. What is V reference? Give you a few minutes for the rest of the students to solve this as well. Our class is until 10:20, yes. I was just looking at this back and I was like, we still at 9:30. So using this equation, what did you get? Okay. V reference would be V out, which is actually our saturation voltage as well. So it's going to be 5 times 15 over 15 plus 10. So it's going to be 75 over 25. Am I correct? Which gives us 3 volts. So the reference voltage here would be equal to 3 volts. We can see that the positive or upper reference voltage, positive V reference, the maximum positive volt value of the voltage at the inverting input, is given as positive V reference is equal to beta V saturation, while the negative or lower reference voltage, negative V reference would be negative V saturation beta. So if Vn exceeds positive V reference, the output switches states and the output voltage drops to its negative DC saturation voltage. Likewise, when the input voltage falls below negative V reference, the output switch state once again, switches state once again, and the output voltage will switch from the negative saturation voltage back to the positive DC saturation voltage. The amount of built-in hysteresis given by the Schmidt comparator as it switches between the two saturation voltages is defined by the difference between the two trigger reference voltages, as V hysteresis is going to be positive V reference minus negative V reference. V hysteresis is actually the voltage that we see between this. We have a switching gap between these two. If the voltage is between these positive and negative V references, we're going to have a transition period. And one thing to keep in mind, I want to explain this and then get back to this, is that since we have a non-ideal op-amp, we don't immediately switch between its positive and the negative output, saturation output. We always have a linear transition between them, or we call it a linear, normal linear region. And this actually depends on our several factors, including the slew rate. You remember the slew rate, it's the speed of which the op-amp could switch states. That makes a lot of, this is very important here. If you have a op-amp, ideal op-amp with a slew rate of infinite, the states would immediately change from negative to positive or positive to negative. But since we don't have an ideal op-amp, it usually have a transition. So for an ideal op-amp, it's going to look something like that. It immediately goes from negative saturation point to the positive saturation point. Okay, I think it's enough for today. We're going to do sinusoidal to rectangular conversion on Thursday. Thank you so much. And let me know if you have any questions. Email me with any questions you may have.